Hi everyone, welcome back. Today we will take a look at the process part of our 2D finite element code. In the last session, we learned how to discretize a domain into a uniform mesh and then again a uniform mesh with a circular void. So today we will use those to do the process part of our code. And also you can think of the last session as the pre-processing part. And this video, along with the first video, the element-wise stiffness assembly video, they make up the processing part. So let's begin. So what we want to do is, normally I like to go over a pre-written code so that it's both faster and I think easier to follow for you. However, today I will not do that. So, and the reason for that is you will see that this process part of our code is quite similar to the first project. So we will copy some of the files we had from the first project and then alter some of the parts of these files to fit the needs of the 2D code now. So let's begin. So here I should have the code from the first project. So I will copy the runner file now and paste it here. Okay. So let's see what we have. So we don't need these right now as they are not assigned as an input to the functions we have. Remember, we assign the material parameter inside our constitutive function, so that's where they come into play. And see that we have our node list and element list. Previously we had manually entered them, but today we will use one of the functions we had written in the last session. So let's actually go back. So here I have the functions. Let me copy void mesh. So it's the one with the circular void, and again paste it here. And let me copy this. Okay, now we have our node list and element list. But we also should define our input, so let me do that. So we had D2, QU, 4N, and also D2, TR3N. Okay. So now we have our, here we have our node list and element list, and our pre-process part is done. So we are now at the process part. Okay. So we had our assign BCs function, and we will need to manipulate it such that we can assign different boundary conditions. So 3 boundary conditions to be exact. So the first one we have is extension. So in extension we want to, for all of these 3, by the way, we want to assign a magnitude of 0.1 for the unit square we have. Okay, so for extension we want to move these nodes on the left side of the domain by 0.1 units to the left, and also move the points of on the right side of the domain 0.1 points again, 0.1 units on the right. And for expansion, we do something similar in both directions. And then for shear, we just move the top side while the bottom side is fixed. Okay, so our assign BC's function should be able to do that. And well, so we should be able to differentiate between the types of deformation we have. So let's actually define a BC type, and it can be either extension, expansion, or shear. So and our, well, I should have written it here instead, I think. And our assign BC's function should take the BC type as an input. Okay, so let's actually copy the assign BC's function from the first project. And let's see what we are dealing with. So again, BC type. Yes. So as usual, we define our number of nodes and PD, and nothing changes. So again, the rows of node list and the columns of node list. And we initialize our extended node list. So it still has the same layout as the first extended node list in the first project. So the first two columns, or the first PD columns, are the node list. The second ones are the boundary conditions, then temporary degree, global degree, displacements, and forces. So we again initialize our extended node list as such. So PD times 6, as we have 6 types of columns. And then the first 2, or maybe 1 to PD columns should be our node list now. So we write that. And so what we did previously was we have a loop over the number of nodes, and for every node, so we knew the different coordinates of every node because we had manually entered them. We would check every node specifically and then assign its boundary condition. However, that would be very inefficient. I mean, now we will have tens of, maybe hundreds of nodes, so we cannot possibly check for the coordinate of every node and then assign the boundary conditions. It doesn't make much sense, right? So what we do is we use again a coordinate check. However, we do not check for the specific coordinates of the nodes. So for example, for the extension case, we want the left side to move to the left by an amount, right? So if we can identify the nodes here on this line, that would suffice. And we know that in the previous video we had put this corner to the origin, so the x coordinate of every node on this line should be 0. And similarly, every node on this line should be at D1. So we can differentiate between nodes and assign specific boundary conditions by using this coordinate check. So let's get rid of these. And then, well, we should also differentiate between the BC types. So let's first add a switch for our BC type. And for the case, let's check extension first. So we have our for loop and then another case. So expansion, and then lastly shear, right? Okay. And in every well, let me put that later, but for every case we should have a loop over the number of nodes. So yeah. So now first let's check for this line. So for every node, if the x coordinate of the node is 0, so what is the x coordinate? We can use the node list for that, right? If nl comma 1 is equal to 0, right? Or actually let's call the CNL to make it coherent. What we should do is we want these nodes to be Dirichlet type, right? So remember our BC column is PD times 1 for the x direction. So we say that ENL I comma, now it's PD plus 1 is equal to 1, right? Oh, wrong, minus 1. So it's a Dirichlet type boundary condition, so it must be minus 1. Okay. And similarly, our y coordinate should also be minus 1, right? Because we are also fixing it in y as well. So yeah, we are taking these nodes and we are just moving them to the left. So we are fixing them on their initial positions in y. Okay. So now that their boundary conditions, or well, the boundary condition types are established, we can actually input the amount of displacement. So again, let's copy this. This time it should be, now we are giving assigning displacements, right? So for the x1 it should be 4 PD times 1, because we are skipping 4 columns. 4 PD, sorry, plus 1. And again, similarly 4 PD plus 2. And I said on this column here, on this, well, side, we are moving them to the left by a magnitude of 0.1 units. So their x should be now minus 0.1 and their y should be 0. Okay. And then let's have an else if. So now we're done with this side. So let's take a look at this side. I want to copy these all again, paste them here. And so this time we should be checking if the x coordinate is d1 or not. Okay. So, but the problem with that is in our assigned BC we don't take d1 as input. So So now we know, because we know our domain is 1 by 1, it's a unit square, we can actually input 1 here. But in your code, you should take an input D1 and stuff, or maybe you can actually extract it from the node list. So however you want to do it. But you can't just enter 1 now. In your code, you should be able to change these, so mind that. And again, our boundary conditions are replaced. This time this should be plus 0.1 and this should be 0 again. Okay. And lastly, else. And let me paste this, get rid of this part. Else, it means that we are anywhere but these two fixed boundaries. So they should be free nodes, right? They should be free to move. So thus they must be Neumanns with 0 forces. Okay. This part isn't really necessary, they're already 0, but still. And we can now move on to expansion now. Okay. So again, in expansion, we should have a for loop over the number of nodes. Okay. And now what we want to do for expansion is, again, for the magnitude of 0.1, what we will do is, for every node on the boundary, we will take whatever coordinate that node was on initially and multiply it by 0.1. So, for example, this node, it's on 0 and 0, so it won't move anywhere. But this node is on 1, right? 1 at x, 0 at y. So at y, it won't move again, but at x, it will move 0.1 units to the right, because 1 times 0.1 is 0.1, okay? And so this corner will move 0.1 to the right and also 0.1 upwards. So that's how it works basically. So now we will need to check for these sides and these sides as well. So let's actually manipulate these two first. So this was checking for this side, remember? So now it should be again Dirichlet boundary conditions. However, this should be not minus 0.1, it should be 0.1 times its initial coordinate, which is ENL comma 1, right? The x coordinate. And we do the same thing for y. So let me copy this and just make this too, such that it corresponds to the y coordinate. Okay. And this happens for every corner. So let me just paste it here. And then copy these two. So now we're checking for the, let's first check for the bottom side. So again, an else if. And now we're checking for the y coordinate. So the y coordinate of the nodes on this line is 0, right? So ENL I comma 2 should be 0. And everything stays the same. And similarly, now I comma 2 should be 1, because every y coordinate of every node on this line is 1, right? And else, so the nodes inside, they're all free Neumanns. Okay. And then lastly, for shear, so let me for shear, let me copy this. Okay, so Now we want to do two things. First, we want to fix the nodes on the bottom to their initial position. So they should be 0 directly. And the nodes on the top side, they should move to the right by 0.1. Okay. So let's actually do that. So now if enl I comma 2 is 0, so we're again at this bottom side. Directly, this should be 0 too. So fixed to their initial positions. And then if I comma 2 is 1, so we're at the top side now. Again, directly. X should be 0.1, Y should be 0. Okay. And then else, again, the free nodes, they're in 0 Neumanns. So let me check and okay, it looks fine now. So after we assigned the BCs here, we will need to assign their temporary degrees and then global degrees, right? And nothing changes in that algorithm. So we had written the code for that in our previous video, and it's quite straightforward. So we're checking if the node is Dirichlet. If it is Dirichlet, we are decreasing our degrees of constraints, and we are writing it as our temporary degree. And if it's a Neumann, so else, we are increasing the degrees of freedom and writing it to our temporary degree. And in the end, our global degree is if our original degree was plus, so if it were a Neumann, it will be the same thing. And if our original degree was negative, so it's a Dirichlet, it will be the absolute value of the temporary degree plus the degrees of freedoms. So yeah, we have that basically here. So that's how we assign our BCs. Nothing new. So now we're done with assigning our BCs. We have our extended node list, our degrees of freedoms, our degrees of constraints. We need to assemble our stiffness now. So let's again go to the old files and then copy the assemble stiffness file, and then see what we change there. So first of all, let's get rid of these ENAs. You will need to have them as input, but I won't do that. I think you can figure it out yourselves. And so let's see what we have. Again, we initialize everything, our global stiffness matrix, so the big one, and then we called on our element stiffness for every element, because we have a loop over the number of elements. So nothing new. Again, this is just as old code. So the only thing we change here is this element stiffness. So we have this function, right? In the first video, let's go back to the stiffness video. We have our stiffness.m file. Let me copy that next to the ones we have now. And then open that. Oops, sorry, yeah. So we have a function called stiffness. And remember, it calculated the stiffness for either a 4-noded quadrilateral element or a 3-noded triangular element. And this function is what we will call now. So in our assemble stiffness function, this element stiffness becomes our stiffness function. So Or if you want, you could change this name to element stiffness, but it doesn't really matter. So now the inputs should change, right? We have x and Gauss points per element. So what were these two? X was the coordinates of the particular element, so the coordinates of the nodes of the particular element. And this is just what you assign for your specific element, right? So we said it could be 1 for 3 noded, or it could be either 1 or 4 for the 4 noded one. So we should change our assemble stiffness such that it calls on our stiffness function correctly. So now let's see what we have. So this small NL, it's the node list of each element. So EL I, 1 to node per element. So it's taking every node of the ith element and storing it. And from that, we should extract the coordinates of every node. And specifically, we should do that in the format of x. And let's see what the format of x was. So this is again the code we had in the first video. So we have x coordinate, y coordinate, x coordinate, y coordinate. So we have node pairs, coordinate pairs for every row. We should, using the small NL, we should have the coordinates of the specific element in this format and then feed it to our stiffness function. So let's do that. So let's call the first input x again. And so we should have, first we should initialize it, x equals zeros, PD, node per element. Okay, so again, nothing new here. So node per element, and PD is 2. So we do basically that. And sorry. Yeah, that is quite nice of you, Ekim. Let me just open it again. Well, yeah, okay, not this one. Obviously, we should have copied it here. So this one, okay. And we don't need this anymore, so I'll just close it. And we were at the assemble stiffness. Okay, so we initialize our x. And let's actually fill it. So for I equals, well, not I. What do we not use here? I think we don't use j. So for j equals 1 to node per element. So x I, should be equal to ENL. We have ENL, right? Yes. Or maybe node list, it also works. ENL I, 1 to PD. So what we're saying here is for every node of the particular element, so the ith element, this should be j, by the way, sorry about that. We should, for the jth row of x, we should write the coordinates of the jth node. And this is wrong. This is very wrong. So what should actually be here is NLJ, right? Because we're not looking at the jth. We're not looking for the jth node of extended node list. We are looking for the jth node of NL. Okay, so and then we feed it into our extended node list. Okay, so that's how we fill out our X. And lastly, we should also have our GPE, right? So let's just write an if condition here. If our node per element is 3, our GPE should be 1, and else if for our GPE, let's make it 4 now. You can change it later. It can be 1, 2, right? So you can do that yourselves. And so now we should be all set, I think. Just let me fix these. And yeah, it looks okay. So if we go back, what's left is our assemble forces and displacements and our update nodes. And I'll just delete these for now. So we're done with the assemble stiffness. Let me save it. Stiffness 2. I think we didn't change anything there. Assign BCs and void mesh. So let me just get rid of them. And then assemble forces. So let me again go back to the first project files and then copy assemble forces and displacements. And paste them here. So for assemble forces or displacements, and remember they were quite similar, nothing changes, not a single line. So what we did was we are checking for whether the prescribed force is Neumann or not. And if it is, we're just assigning the prescribed force to FP. Okay. And similarly, so we're checking for the assemble displacements, we're checking if our boundary condition is Dirichlet or not. If it is, we are assigning whatever magnitude of displacement we have to our UP. Okay, so I'm not going over them in detail, I know, but I think you know them already, so we can just move on. So again, this part, these should also be familiar to you. We are this is the reduced stiffness matrix, and using that we can calculate our unknown displacements and unknown forces, as you know, as you have seen in the first video. And the only thing left is to update our nodes. So again, let's go back, take the update nodes function, and again paste it here. So here in the update nodes function, again we don't change anything, so everything stays the same. We're just now checking the boundary conditions again. So if our boundary condition is a Neumann, if we have assigned a force, it should have an unknown displacement, right? So we are assigning that now calculated unknown displacement inside its place in the extended node list. And similarly, if our boundary condition is a Dirichlet, its force should be unknown. So we are assigning the newly calculated unknown force in our extended node list. And that's pretty much it. So let's run this and hope it, well, runs. And it didn't, so what's the problem? Assemble stiffness. Okay. Okay. So this should have been like this. I think. But I just want to check the format of the x coordinates again. Okay, so rows correspond to the nodes and columns correspond to the coordinates. So yeah, number of nodes should be rows should be node per element actually, and this should be PD. So we should be good now. Let me run it again. Okay, we're printing something. So where do we have? Yeah. Yeah. Okay, so yep, looks good. So now we have our unknown forces and displacements, and we can move on to the post-processing. But before that, I want to make some remarks. So well, the first thing is in assemble stiffness, or actually in the small stiffness element stiffness assembly, this stiffness function. Remember that we have this constitutive function we use. So here we're assigning the material parameters E and nu inside this constitutive function. So in your project, you will be asked to model a domain with an inclusion. So think of it as again a domain with a circular void. However, now this void is not empty, it's filled with a different material. So the nodes inside this region, this circular region, should have different material properties now. And you should have an if condition that checks for that. And that's for you to discover yourself how to do that. And so let me think what else. So about the boundary condition types. So as I said, all of the boundary conditions here, they have the magnitude of 0.1. However, for extension, instead of extending it from both sides, if we had fixed the left side and moved only the right side, it would still be the same type of deformation. But for them to be equal, now these nodes on the right should move to the right 0.2 units. So so this is just how we define these deformations. Okay, so this 0.1 magnitude, it's not something that's, you know, set in stone. What we define as 0.1 is actually stretching it to 0.1 on both sides. And you could have, again, fixed the left side and then stretched just the right side to right by 0.1 units and called that extension as an 0.1 magnitude. Okay, so it's a matter of preference. So that was another comment I had. So I think this is basically it. So let me show you my extended node list in case you want to check yours and to compare with mine. So just some rows and columns. So see that most of the last two columns are 0. And remember, our last two columns were forced. So these are actually the free nodes, Neumann nodes. And this was an extension case. So most of the nodes are free. And they all have corresponding displacements. Right, so yeah. Recording this after I reviewed the video, and I realized that I forgot to comment about this part in our stiffness matrix, stiffness function. So remember in the first video how we calculate this stiffness. We have a 1/2 factor here if our element type is triangular. And if it's not, we don't have that. So when I was running the previous example, this should have been like this. So the extended node list I have shown you is wrong. So let me run it again. And now you can see the one with the correct values of forces and displacements. So if you want to check. Yeah. Now we can move on to the post-processing part. So I'll see you in that video.